Good morning, guys. I hope you're all doing well today. I just wanted to work through some of these 2.4 notes with you today. So just a quick reminder, we had started doing this in class on Thursday and then ran out of time. But if you remember, we finished up with example 3 on Thursday, and we had found that if we again, on the previous page, we drew all our rectangles under the curve so that we got the underestimate of 6.48 square units for an area under the curve. And then in this part right here, we drew all our rectangles so that they extended beyond the curve. So we got an overestimate of 8.08 square units as our area. And that was when we divided it into 5 sub-intervals. So we were looking at the interval from 0 to 2. We wanted to find the area under that curve, which was 5 minus x squared, or negative x squared plus 5. So we divided it into 5 sub-intervals at their suggestion. And those are the areas that we came up with. And so what we started to talk about at the end of the class was, how can we generalize this? How can we apply this to other problems? So we started by saying we can generalize it as follows. Take some plane curve, as in two-dimensional, and it's bounded above by the graph, right, of some non-negative continuous function. Again, things change if it's not if it is a negative function, or if it enters into negative territory at some point. So for right now, we're just going to look at non-negative, and again, the continuity would mess things up too. So we're specifically looking at non-negative continuous functions, which we call f of x, as shown in this, which in the textbook is 4.10. And it's bounded below by the x-axis, and in the left it's bounded by the line x equals a, and to the right it's bounded by the line x equals b. And so we're trying to find the area of the shaded in region. And so what we said was, let's approximate the area of the region. We're going to begin by subdividing that interval, AB, into n subintervals. And so we reflected back on what we did right here and how we found our 5 subintervals. And that was, we found the length of this, the region, or the interval a to b, and we divided it into our n subintervals that we're looking for. So b minus a over n, and that is going to be our change in our subintervals that we would do, that we would call this the width of our rectangle. All right, and that is shown in, this was figure 4.1. So we would just call this x sub n. It has a length of delta x. All right, and then the endpoints, we already filled this in, but because we rushed through this, I just want to make sure that you're okay with it. So we start with a, right, and then we add 0 delta x's on. All right, because again, we're going to keep going through and we're going to add delta x, delta x, delta x, that width that we found right here, until we get to the endpoint b. Right, so this is equal to a because we're adding nothing on, but we would also call this x sub 1, or I'm sorry, x sub 0. And we can say that then it is less than, right? So again, what we've just done is we've started here, we've added on this delta x amount, and we're calling this interval x sub, we're going to give that endpoint x sub 0. And then we would do the same thing, and we would get a plus 1 times delta x, and we're going to call that x of 1. And then we would do a plus 2 delta x's, and we would call this x of 2. And we would keep going until we did this n times, and we would take a plus n of these delta x's. And this would end up as x sub n, but we would also call it b because we finally get to this endpoint b when we do that. All right, and we commented that within each of these intervals right here, that there is going to be a minimum value and there's going to be a maximum value. All right, and that point in there, whatever this is, so here this would be like our capital M sub I, that's going to give us the maximum value on this interval. And then we also have a lowercase m sub I on that interval. All right, so we subdivide it, we find the maximum when we want to overestimate, we find the minimum when we want to underestimate, and then we would call those, what we have down here, f of m sub I is the minimum value of f of x on the ith interval, and f of m, capital M sub I, is the maximum. All right, so again, we ran through this on Thursday right at the end of class, so hopefully it wasn't too confusing. Hopefully that kind of just refreshes your memory and clarifies anything for you. Okay, so on the next page then, we're going to still just continue with this, trying to just give a generalization or procedure. So then we say, next let's define an inscribed rectangle as lying inside the ith subregion, and a circumscribed rectangle extending outside the ith subregion. So remember, when we did this before with our curve right here, when we kept it completely inside, that was the inscribed, and then when we went beyond that, let's say to right here, that was circumscribed. All right, the height of the ith inscribed rectangle is going to be, again, we're going to choose the lower value right here, so it's the f of little m sub I, because that's the minimum. That's how we get an inscribed rectangle, is that we choose the absolute minimum value in there, and then to get the circumscribed rectangle is that we choose the highest value in that interval. All right, if we choose anything in between the lowest value and the highest value, then it's not inscribed and it's not circumscribed. It's something in between. We want it either completely under or not, or just completely above. All right, so we don't want something in middle ground. We want one or the other. All right, again, if we choose something other than this value right here, let's say we choose this value right here, then we're going to get something that's partially above and partially below. Same thing, if we choose this value right here, we would get the height of that would be down here. Sorry, my picture's not big enough for you to see that. Let me just do it right here. All right, if I were to do it something like this, and let's say this is the interval I'm talking about. All right, and let me make this a little bit less flat right here. Okay, let's say we do something like that. All right, so if I were to choose this point right here, this x value, that is not going to give me, and I go horizontally from whatever the value, the y value is right there, I'm going to get part of it under and part of it over. All right, so it's not fully inscribed because I've got a little bit hanging out, and it's not fully circumscribed because I've got some little bit here that's still inside. So we want to make sure that we're picking either the minimum value or the maximum value. That's what we've done in the past. We're going to see that that doesn't completely matter, but for right now, we're going to just stick with that. All right, so for every I, again, I going from 1 to 5, I going from 1 to 20, whatever, that's the number of subintervals we get. Or, you know, the subintervals that we're going through. The area of the inscribed rectangle is less than or equal to the area of the circumscribed rectangle, all right? So the inscribed has to be smaller, probably, but there would be some cases, let's say if you were doing some shape that were rectangular, something where it didn't make a difference whether you were choosing the minimum or the maximum because they were both the same. So it's telling us that the area of the inscribed rectangle, so again, remember this from our work on example 3, that we would take the height and then multiply it by the base. All right, so that's going to give us the area of the littler rectangle. Has to be less than or equal to the area of the circumscribed rectangle, the bigger one. So this was the height and this was the base. All right, so hopefully that makes sense because that's exactly what we saw when we did this in example 3, that the area of our inscribed rectangles were all less than or equal to the area of our circumscribed rectangles. Okay, hopefully you're feeling okay about this. All right, the sum of the areas of the inscribed rectangles is called the lower sum. All right, again, lower because all the areas would be smaller. And the sum of the areas of the circumscribed rectangles is called an upper sum. right? So again, if we go through here and we say, all right, again, this is exactly what we did in example 3. We found the height times the base, and that was the area of each individual rectangle, and then we did that for the number of rectangles that we had. So in our particular case, in example 3, this was 5, right? We had split it up into 5 subintervals. Right, same thing, and this is on the top of that second page there, where we found the upper sum. This was our height because this was the maximum value that we had on each interval. So when we chose the right endpoints versus the left endpoints, and then this was the base. All right, so then the sum is just the area of all those rectangles. Okay. All right, so then from this example right here, and again, I just put this in here from your book, you can see that the lower sum, which we call lowercase s sub n, is less than or equal to the upper sum, which we call capital S sub n. The actual area of the region lies somewhere in between the two of them. Again, that's what we said for example 3 right here, when we said our overestimate was 6.48. I'm sorry, our underestimate was 6.48. Our overestimate was 8.08. The true area was going to be somewhere in between there, right? Bigger than 6.48, smaller than 8.08. All right, so that's exactly what it's saying right here, that the area, the true area of our region is somewhere between those two sums. All right, so again, here's a picture where they show the area of the inscribed. So notice how all of them are completely under the curve. None are partially sticking out and partially hidden beneath. They're all completely beneath. And then here is our upper sum, our overestimate. Everything is sticking out somewhere here. All right, nothing is hiding under the curve. All right, and here is the true area of the region. All right, so the area of this is all of these rectangles, the part that's underneath the actual area plus these extras, and here the lower is just all of these rectangles, and so we're missing out on these parts right here. All right, but we want the true area. Okay, again, all of this kind of background is bringing us up to some other examples here. So hold on, let me get back to my page. Okay, so we're going to do an example here, and we are going to look at an upper sum and a lower sum, but the difference that we're going to do here between example 3 and this example 4 is, notice it doesn't tell us to break it up into 5 subintervals or 10 subintervals. We're just going to do this in general. All right, so the first thing we're going to do is begin by dividing. Sorry, I can't even remember if I read this. Find the upper and lower sums for the region bounded by the graph of f of x equals x squared, the x-axis. So again, remember it says the curve, the x-axis, and our a and our b. And again, also notice this is continuous and non-negative. All right, so all the information we were just talking about applies to what we're getting ready to do right now. All right, so begin by dividing this interval that we're given, 0 to 2, into n subintervals. All right, again, not 5 like we did in example 3, but just n. And then what are the lengths of each of these? Well, remember, it says that if we want to find the length of the subintervals, we have to take the two endpoints, the greater, which is 2, minus the lesser, which is 0, and divide it by how many subintervals we want. So we want n subintervals. So that tells us that each subinterval should be 2 over n. Good? Okay, so then we're going to choose for the lower sums, we're going to choose the left endpoints. All right, that's because this is increasing, we want the left endpoints. If you remember with our example 3, because it was decreasing, our lower sums actually came from using the right endpoints. And you can go back and just look at that if you want to pause the video and go back and look to see that in example 3, when we wanted the lower sums, we chose the right endpoints, and for the upper, we chose the left. But now because this is increasing, we're going to reverse that. All right, so the left endpoints, All right, and again, remember what it said to do. It said, and again, this is on the bottom of 2 pages ago, this one right here. All right, where we're going to set up the endpoints of the intervals. All right, so we take A and we add, let's see, the width of our interval. And we're going to do I minus 1. If you remember, go back and pause if you want for just a second and go back and remember we had this conversation in class. We were trying to figure out how to name the left endpoints. It was easy to name the right endpoints. We just started with I plus 1 and so forth. But this we had to go backwards 1. So we're going to start out with our left endpoint, which in this case is 0. And we're just going to, here is the width. All right, that's our delta x. And then this is going to go through and count for us so that we get all these different endpoints that we want. So we're going to start at 0 because we're going to do 1 minus 1 is 0 times 2 over n, and we're going to add that to 0. And then we'll move I up to 2, so then we get 2 minus 1, which is 1 times n over 2 over n, we get the second one, and we would keep going through like that. Again, we start at our endpoint. This is the width, our delta x, the width of each interval, and then we just want to make sure that we get the left endpoint, so we do the I minus 1. And as I increases, we're going to go through and we're going to get each of the left endpoints. All right, let's just clean this up though. All right, the 0 is going to do nothing for us. And then we're just going to have 2 times I minus 1 over n. Actually, there's not a lot of cleaning up. You could distribute, but I would say for right now, let's just leave it like that. Okay, so then these are the endpoints. So then what we need to do is set up our sum. So we're going to go I equals 1 to n. And again, remember we need the height times the base. All right. Each base, each width is what we decided right up here, 2 over n. The height is going to come from doing f of this value right here. Remember, these are our left endpoints, so it's going to be 2 times I minus 1 over n. All right, again, pause anytime you need to go back and look at example 3 to see this is exactly what we did right here. Okay. Hopefully you remember to do what to do next. I'm going to stop and let you think about that for a second. And I'm going to put lowercase s of n here because this is the lower sum. Okay, did you think of it? All right, this is where we take and we plug this, the 2 times I minus 1 over n, into our original equation, which is the x squared. So right here we're going to get 2 times I minus 1 over n squared, because our function is squared. So that gets rid of the f, and then we still have this 2 over n. Okay, I'm going to pause here for a second to restart the video. Okay, so now we need to expand this using our different rules. Actually, there's a couple different things we could do, but for right now, let's just do this. So we're going to take and multiply that out. All right, so the 2 squared is going to give us 4. Then we've got I minus 1 squared. That's going to give us I squared minus 2I plus 1 over n squared. Sorry, I forgot the sigma. And then we still have this 2 over n. Right, I'm just going to choose to combine the 4 and the 2 to get an 8. and then the n and the n squared to get an n cubed. And I'm going to write this, but again, this is one of those steps where you can choose to write it or not write it, because in just a second we're going to yank that guy out. So we've got I squared minus 2I plus 1 times that. All right, I've pulled out everything else that's not involved with an I. Again, because the I, we're going to have to use our summation formulas to write that in a shorter way. Okay, so let's yank this guy out. So we're going to end up with 8 over n cubed times the sum I squared minus 2I plus 1, I ranging from 1 to n. All right, think about what you should do next. Okay, so hopefully you remembered that we would use our formulas to break this up. So we've got 8 over n cubed times, again, this 8 over n cubed is going to apply to all three sums that we create. So we've got I equals 1 to n of I squared minus 2 times I equals 1 to n. Again, I did two steps right there. I pulled the 2 out and I did the summation of I. Plus summation I equals 1 to n of 1. All right, then using those formulas that we've been using, we're going to end up with 8 over n cubed. Then we would get, this formula was n times n plus 1 times 2n plus 1 over 6. Minus 2 times, that was n times n plus 1 over 2. And then this one just ends up giving us n. All right, then we get 8 over n cubed. And then when we multiply this out, actually, I did this all on scrap paper because I knew I was running out of space. So when I multiply all of this out, I end up with, and in fact, I'm going to ask whoever's running the video here to pause it and let you figure out what that is first. So just expand all that and combine everything. So pause the video for just a second and then come back and I will have the answer for you. Okay, so it should be 2n cubed minus 3n squared plus n all over 6, which is the same thing as, if we cancel things, again, pause for just a second and see what you get. We're just going to multiply these two together. So cancel what you can from the n cubes, from the 6 and the 8 and so forth. Okay, so canceling this, or just canceling the 6's first as an intermediate step, we would end up getting 4/3 n cubed and then 2n cubed minus 3n squared plus n. And then if we distribute that, so hopefully you did both of these at the same time, so you would have gotten 8/3, the n cubes cancel out, minus 4 over n plus 3, plus 4 over 3n squared. And this is the lower sum. Easy, right? Piece of cake. Okay, so I'm going to ask you to pause again. And well, actually, let's do this. Let's set up the right intervals, and then I want to pause and see if you guys can do on your own, following what we just did right here, the upper sum. So again, in this case, we're going to use the right endpoint because that's where the maximum occurs, since this is an increasing function. Right, so let's just set up the right endpoints and we'll set up the sum, and then I want you to work through it. All right, so the right endpoints. That would be 0, because again, that's our A. And then we add on the width of our interval, and then we have to decide how we're going to get that right endpoint. Again, for the right endpoints, it's just a plain old I. For the left endpoints, we had to do the I minus 1, but for the right endpoints, it's just I. So we end up with 2I over n. All right, so that is our delta x. Sorry, that's not our delta x, that's our x of I. Our delta x, which we already had up top, is just the 2 over n. All right, so I want you to pause, and I want you to see if you can go through here and set up your upper sum. So capital S of n, making sure that I'm still actually in the screen. So set up your upper sum just like we did with our lower sum right here, but we're just going to choose a different value here because we got a different x of I. All right, and then I want you to see if you can come up with that formula for the upper sum. Right. Okay, so for the upper sum, hopefully this is what you got. We go I equals 1 to n. Now our upper, for our circumscribed, sorry, I didn't put that n up before. It's f of big M sub I, which again is our right interval. So it's going to be, that x value is going to be 2I over n. So we're going to put that in. So we're going to get I equals 1 to n of f of 2I over n. That's our height times the width or the base, which is 2 over n. And then I plug this in, the 2I over n, plug it into our original function, which was the x squared. So this is just going to turn into I equals 1 to n of 2I over n squared times 2 over n. So let me erase this because that looks like it's right in our formula. All right. So then we square that out. So we end up with 64. No, sorry, that's a 2. It looks like an 8. Okay, so then it is I equals 1 to n of 4I squared over n squared times 2 over n. All right, again, feel free to skip some of these steps if you can square this and multiply at the same time. I equals 1 to n of 8I squared over n squared, no, n cubed. All right, this 8 over the n cubed is a constant. Again, I is our only variable when we're doing these summations. N is a constant, we just don't know what it is. We're just choosing, we will later randomly choose n. Or we could later randomly choose n when we put n up here. All right, so we pull that out. So we get the 8 over n to the third summation I equals 1 to n of I squared. This one's nice. It's not, doesn't have all those different pieces that the one above here did. So we just get that single I squared. And again, if you remember our formula, we've got 8 over n cubed, and then this is n times n plus 1 times 2n plus 1 over 6. And then when we multiply that out, again, for space saving purposes, I did this on scrap paper, but it is 2n cubed plus 3n squared plus n over 6. Eventually, you're just going to remember this because that's always what's going to happen when you multiply out these quantities for an I squared. All right, and then we would just combine things, cancel, simplify. Again, for space saving purposes, I'm just going to write out what I got. Ultimately, I ended up with 8 over 3 plus 4 over n plus 4 over 3n squared. And this is our upper sum. It's an overestimate, again, because we used our right endpoint, so we chose the higher, the larger M, capital M values. And here we chose the left endpoints, and so we got the lower values, the inscribed rectangles. All right, so here's what we just want to comment right here about, and this is kind of the cool part right here, because before in example 3 we found an overestimate and an underestimate. Here's what we're going to note. So note that lowercase s of n is 8/3 minus 4 over n plus 4 over 3n squared, which we already saw from our work, our just general work that we did. Where was that page? Right here. We noted that the lower sum is less than or equal to the actual area, which is less than or equal to the upper sum. So we're going to say that same thing here, but we're just going to take out the area part. We're just going to note that the lower sum that we found is less than or equal to the upper sum. So here this is less than or equal to our upper sum, which is 8/3 plus 4 over n plus 4 over 3n squared. Hopefully that's not a surprise because everything is the same except that term right there. This is a minus, which would decrease the value, and this is a plus, which would increase. So this is our upper sum. All right, now the cool part right here. And again, I was so sloppy in writing this that I am going to run out of space. But I want us now to do something which we have not done, and that is take the limit as n approaches infinity of our lower sum, which is 8/3 minus 4 over n plus 4 over 3n squared. All right, so as we let n go to infinity, what happens to 8/3? Just stays 8/3. What happens to minus 4 over n as n goes to infinity? Hopefully you realize that goes to 0. Right, same thing here. As n goes to infinity, what happens to 4 over 3n squared? Again, as n goes to infinity, this goes to 0. So the limit of our lower sum, as we let n get really big, as we choose not 5 subintervals or 10 subintervals, but infinitely many subintervals, we get 8/3 as our area. So this is our lower sum, right? Because again, before we just chose a finite number, now it's saying make as many intervals as you can. The more intervals we get, the more accurate our area is going to be. So make as many intervals as you want, infinitely many, and the area is going to go to 8/3. And then if we do that again, if we take the limit of our upper sum, capital S of n, again, I'm running out of room, otherwise I would write all the little details here. It's the limit of our upper sum, which is 8/3 plus 4 over n plus 4 over 3n squared. Right, the limit as n goes to infinity of 8/3 is still 8/3. The limit as n goes to infinity of 4 over n, still 0. And same thing here, the limit as n goes to infinity of 4 over 3n squared, also 0. So our upper sum, again, this is our capital S sub n, and this is our lowercase s sub n. The limit of each of them, as we let our number of rectangles go to infinity, both of them give us an area of 8/3. That means that the actual area has to be somewhere in between them. Well, there is nothing in between 8/3 and 8/3, so the actual area under the curve of x squared from 0 to 2 is 8/3. All right, so before we were able to get an upper sum and a lower sum, but now when we find both of them and we let n go to infinity, we take the limit, let n go to infinity, we find the actual area. All right, well, I think that's probably all we have time for right now. All right, bye.